I think it's like 1, 2. I need to figure out whether
Okay. Okay. All right. Get back to things. All right. So yeah, we're going to turn to polynomial IOPs based on the sum-check protocol. Definitely my favorite tool in SNARK design. ML, all you need is attention. SNARKs, all you need is the sum-check protocol. Sorry. Attention is all you need. Sum-check protocol is all you need. I want to give a couple pieces of intuition before we see the sum-check protocol about why it's useful. Okay, so one piece of intuition is cryptography is expensive, which just means is if you want to commit to a lot of data, you can do it. The commitment will still be small, but computing that commitment will be slow. Okay, on top of that, the more data you commit to, the more work you as a prover have to do to prove that that data is well-formed, that you committed to the right data and not some garbage data. Okay, the sum-check protocol uses no cryptography at all as a standalone object, right? It's information theoretically secure until you fiat-Shamir it anyway. And this generally makes it lightweight for the prover, right? The prover is just adding and multiplying field elements. It's not hashing, doing MSMs. They're generally lightweight. So in SNARKs, it's the perfect tool to let the prover commit to a minimal amount of data and then prove that that committed data was well-formed. Yep.
Is the hashing more expensive than multiplying?
Field elements can be, yeah.
What's hashing? Like, is SHA-256 more expensive than?
Yeah, so firstly, this
I don't know anything.
So this question is dependent on things like what field are you working over. Let's say we're using elliptic curve commitments because I like them. 256-bit field. One field multiplication, it's like 80 CPU cycles. Okay. I think like a SHA evaluation, I think it's like 70-ish cycles per byte. You can look it up. Okay. They're both pricey, right? We don't want to do a lot of either. Okay. But the deal is like if you commit to less data, it certainly will be faster to commit to, but then if you go about it in a smart way, you'll also be faster at proving the committed data is well-formed. So you kind of win on both ends. So you don't really have to get too in the weeds of how does hashing compare to field operations, even though ultimately if you're building these things, you should get into those weeds. The techniques will win kind of regardless of what the answer is. Other questions? Okay. Yeah, so you can view it as a tool for offloading the hard work of checking that the committed data is well-formed. You offload it to the prover. You force the prover to do that work. And you're not using any cryptography to do that forcing. Okay, so that's one view. Here's another view for why the sum-check protocol is useful. Just looking chronologically, historically, at how things evolved, right? So interactive proofs were introduced first in like 1985 or something. And then PCPs came a little bit later. And then the first SNARKs were built on top of PCPs, right? We saw this morning, the Killian-McCauley framework, right? PCPs, well, they use this univariate polynomials and quotienting, whereas SNARKs use the sum-check, interactive proofs use the sum-check protocol, right? And so, in my view, like one big reason the univariate stuff is so popular in SNARKs today is just because people took the SNARKs we had from the old theory work and tried to make them practical for years. Those were based on PCPs, and so they were using univariate polynomials and stuff. And that does get you SNARKs that give you like the best verifiers, okay? But the key bottleneck today is prover scalability. And there it just, this ultimately really doesn't make sense if you take a step back, this approach of going through PCPs, right? Because what is the hard thing about designing a PCP? It's that the probabilistically checkable proof is non-interactive, and yet you want it to be not too big, right? So the whole game is making that proof probabilistically checkable and not too big when it's no interaction, right? The Killian's transformation into a SNARK brings interaction right back in. Right? So McCauley had to fiat-Shamir it to get the SNARK, to get the N in SNARK. Why did we move the interaction, remove it twice? Right? If we're going to have fiat-Shamir, just remove it once. So we should be treating interaction as a resource to make the prover as fast as possible, and just remove the interaction once with fiat-Shamir. Don't go through this double removal thing. Okay. So these are kind of the best two pieces of intuition I've come up with as sort of before you even see the protocol, why it's useful. But now let's start to see the protocol. Before I introduce it, some preliminaries, multilinear extensions. So if I give you a function whose domain is 0, 1 to the L, and it spits out field elements, a polynomial extends it so the polynomial is defined over field to the L, so it's got a bigger domain. It extends the function whose domain is 0, 1 to the L if they agree where they're both defined. Okay, and so if I give you any function with this domain, there's a unique extension that's multilinear. That means it's a polynomial of degree 1 in each variable. Okay, so here's an example function on 0, 1 by 0, 1. Here's its multilinear extension. Yeah, and you can kind of check it's like linear in each variable. This is a line in each direction, a line in each direction. Okay, here's another extension. Sorry, this is Here's another extension that is not multilinear, right? So like any function whose domain is 0, 1 to the L has many extensions, but exactly one of those extensions is multilinear. Okay, questions about this? All right, I also want to talk about multilinear extensions of vectors. And this just means we're going to interpret the vector as a function with the appropriate, Boolean domain, right? So if it's like the evaluation table, right? So if I have a function of length, a vector of length 8, I'm just thinking of this as a function on 3-bit inputs. And then I can take the multilinear extension of any such function. Okay. I'll also take the multilinear extension of matrices and kind of any object I'm going to take multilinear extensions of in the natural way. Okay, so subject protocol. So the goal is, there's some, multivariate polynomial. This is not multilinear. Okay, it's typically G is built out of multilinears, but anyway, so G is just a low-degree polynomial, not necessarily multilinear, and we want to sum up all of its evaluations, say, over the Boolean hypercube. Yeah, and so, if the verifier wanted to do this on its own, it would have to evaluate G at the 2 to the L points we care about. We consider that to be too much verifier work. So we want a way to force the prover to compute the sum on the verifier's behalf. All right, so at the start of the protocol, the prover sends the claimed answer, and the prover just says, hey, the answer is C1, and now I'm going to move on to round 1. And what does the prover send in round 1? It is a univariate polynomial S1, which is claimed to be this thing. Okay, so this thing is summing over all but the first variable and leaving the first variable kind of unsummed. Okay, so there's like 2 to the L, over 2. It's still a big sum, but every term in the sum is like a degree. Let's say G has degree 2. Every term in the sum is a degree 2 univariate thing. So if I sum up a trillion degree 2 univariate things, I just have a degree 2 univariate thing. It's got 3 coefficients or whatever, right? So the prover sends 3 coefficients to the verifier specifying S1, which is claimed to equal H1. Questions about this? That's round 1. Okay, and so the verifier says, hey, I don't trust you, prover. So let me do some checks, right? First, I'm going to check that S1, what you sent me evaluated at 0 plus evaluated at 1 equals the claimed answer, right? Obviously, if the prover's honest, this will be the case because I defined H1 to have that property, yeah? I left out the first variable, and the final answer sums the first variable as well. And then, right, so the way to think of it is if this check passes, it's like safe for the verifier to believe the original claim as long as it believes that S1 equals H1. But the verifier does not know that S1 equals H1, right? So whenever I have 2 different polynomials and I want to make sure they're the same polynomial, what do? I pick a random point and make sure they agree at that point. So the verifier picks a random point, and it's going to check that S1 at that point equals H1 at that point. Okay, now it can compute S1 at that point directly. S1 was just like a degree 2 polynomial the prover sent it. Like that takes no time at all. But the verifier doesn't know H1. Okay, so we still have work to do in order for the prover to prove what is the value of H1 at this point. Okay, but fortunately, H1 at that point is just this sum. All I did was fix the first variable to R1. Okay, and that's exactly the kind of claim the sum check protocol was designed to prove. So we just iterate. That's it. So in every round, the verifier picks a new random point, evaluates the prover's message at that point. Well, first it checks that the claim from the previous round, is consistent with the new message, and then it moves on to the next round with the fresh random point. And once you sort of pick a random value for every single input variable, you can stop, right? And now the verifier, as long as the verifier can evaluate G at a single point, you can check that final round with no more iterations. Yeah. Okay, so that is sum check protocol, right? It's kind of, I kind of present it in a way where, completeness is clear and soundness, I sort of hand wave my way through. Hopefully it makes, you're just kind of spot checking each round's message at a random point. That's all. So, there's the prover's sending, if G has degree D in each variable, the prover's sending a D plus 1 coefficients in each round or whatever. There's 1 round per variable, and the verifier just at the end has to evaluate G at a point. So it's like pretty good cost for the verifier. Right, and in most applications, this degree D is like 2 or 3, and the number of variables is like logarithmic in whatever statement, the size of the statement being proven, okay? Let's briefly talk about prover time. I don't have enough time to cover, details of the, how to make the prover fast. Also, it's pretty application dependent. Like every time I apply the sum check protocol to a different G, there might be some bespoke work I have to do to make the prover fast for that G. But in general, what's going on is, in round I, the prover's message is, this is it, right? So we're summing over, all variables I plus 1 and up. We've already sort of bound the first I minus 1 variables to random values. And yeah, so this is what we want to compute. And if this is like a degree, D polynomial, it's enough to just, plug in D plus 1 values for xi, right? Like, I can specify a degree D univariate polynomial by telling you D plus 1 coefficients or D plus 1 evaluations. With all this sum check stuff, it's always nicer to work with evaluations and not coefficients. So yeah, so the goal of the prover turns out to be to evaluate G at all points of this form, right? The first I minus 1 variables are already bound if we're in round I. The ith variable ranges, over any set of size D plus 1. And then we need all Boolean values for the last points. Any questions about this? Okay, so yeah, back in 2011 with Kermode and Yi, we gave 2 different algorithms to implement this when G is a product of multilinear polynomials. That setting is sort of implicit in the paper, but anyway. So one is, I call it the dense algorithm. It runs in time 2 to the L. Now this is the number of terms in the original sum. So this is, in a sense, within a constant factor of optimal. Yeah. And what this is exploiting is that in round 1, there are 2 to the L terms. In round 2, there's half that many terms. In round 3, there's half, again, that many terms. So you have a geometric sum in terms of the cost to the prover, and that's just actually dominated by the first term. Okay, so that's one algorithm. The other algorithm, if G is sparse, and by sparse, what I mean is most of its evaluations over the Boolean hypercube are 0. So if most of the terms of the sum are 0, this second algorithm spends time just linear in the number of non-zeros per round. Okay, and so if you have very sparse things, you only pay for the non-zeros. Now the nuisance here is as you go round over round, the sparsity might not fall the way the number of terms being summed falls, right? And so you actually pay in the, kind of in the worst case, sparsity time per round. And so you wind up with, sparsity times number of rounds time. So this is only an improvement if you're sort of sparse enough, fewer than like a 1 over L fraction of entries of evaluations are non-zero. Okay, anyway, so that's sum check and how to make the prover fast. All right, so, we saw how to use quotienting and univariate polynomials for, proving statements of this form. In the univariate case, the claim was, polynomial A times B equals C at all points in some set where that set was a subset of the field. In the multilinear case, the sum check case, the relevant set is always 0, 1 to the L for the relevant value of L. Okay, and so, if these vectors A, B, and C have length n, we interpret them as functions over 0, 1 to the log n, because there's n elements of that domain. Anyway, so that's the right number of variables here. Okay, and so this is a little technical, but very intuitive. We're claiming a whole bunch of values are 0. I guess for time reasons, I'll sort of gloss over that. Here's what's going on. One way to check that n values are 0 is to just take a random linear combination of them. Right? If they're all 0, any linear combination is 0. And if even one of them is non-zero, it's very unlikely that a random linear combination will be 0, right? Like you'd have to get some crazy cancellation. Okay. We're gonna do almost that, except the The coefficients in the random linear combination will not be fully random. They'll sort of be log n y's independent. Don't worry about it. So the point is to get something we can is really nice to apply sum check to. Okay, so just glossing over these details to check that, a of x times b of x equals c of x for all Boolean x, where a, b, and c are multilinear. This turns out to be equivalent to just confirming that this sum equals 0, right? And this thing right here is sort of like giving you like a random linear combination, yeah? Okay. And you can work through the details offline, and they're not that complicated, right? Okay, so all you do is you apply sum check to compute this sum. That's it. All right. And kind of at a high level, there's just the big benefit here is sort of there's no quotient polynomial, right? You're not computing it, you're not committing to it. You're just applying sum check to this nice low degree thing. At the end of the sum check protocol, right, the verifier has to evaluate, the thing being summed at a random point. That means evaluating a twiddle, b twiddle, c twiddle at some point, as well as this eq twiddle thing. And sort of, very similar to the univariate case, the verifier can evaluate the eq twiddle thing on its own really quickly because it's very, very simple. You can evaluate it in log n time. And if a twiddle, b twiddle, c twiddle are committed, the evaluations come from the commitment scheme. Yeah, in fact, we, this has been optimized sort of concretely even more in recent years. And the prover time is just like 6n field multiplications, where n is the number of terms in the sum. So even computing the quotient polynomial would be n log n or something, much more than that. Okay. Now there's more. So we've seen now the prover did not have to commit to the quotient, but there's more benefits beyond that, right? Because in applications with sum check, these ABC polynomials will also not have to be committed. Okay. So there's this nice terminology that this new Binius work introduced, but the idea is not new, called virtual polynomials. Okay. These are polynomials that are not committed, but the verifier can kind of pretend they were committed. Okay, because they're defined in terms of other polynomials that are committed. So when the verifier has to go and evaluate the virtual thing at a random point, if you can, reduce that evaluation to evaluating the actual committed thing with another application of sum check, right? And you can do this as long as you can write, the requested evaluation of the virtual thing as a nice sum of other things. Okay, and so, in snarks for, this funny kind of constraint system people call rank 1 constraints, the little a, little b, little c are kind of related to a committed witness vector by these public matrices. And so, when the verifier has to go and evaluate little a, at a random point, even though a isn't committed, it's no big deal. You just apply the sum check protocol again. And now at the end of that, the verifier has to evaluate the thing that actually is committed at a random point, as well as like the constraint matrices that are public at a point. And for a lot of constraint matrices, they might be very big, but they're very structured, and so the verifier can get this evaluation on its own quickly, and yeah, it gets the evaluation of the committed thing from the commitment. Yeah. So yeah, the point is like not only is there no quotients, there are other benefits too. Other things are not getting committed. Okay. Now you might ask, well, isn't there an extra sum check here, and doesn't that have more cost for the prover? Right? In fact, there's really 3 extra sum checks, one for little a, one for little b, and one for little c. And now we get to another point that I want to kind of give a hint at now, and then I'll emphasize more later, which is especially in snark design in general, but sum check-based ones in particular, you can heavily leverage repeated structure for performance gains. Okay, so we'll see in a lot of contexts, like these constraint matrices, they're like block diagonal, right? We'll see why in like 30 minutes. So you might have the same little tiny matrix, blocks along the diagonal, but you have like a ton, billions of copies of that, right? And in this case, you can actually, it's pretty easy to check, as an exercise offline that the second sum check only has to be over the number of columns in the small blocks, independent of the number of copies of the small blocks. Okay, so for time reasons, I won't go through this, but like I have a multilinear polynomial evaluated at some point here, and I'm claiming that equals some other stuff and the way to verify such a claim is to make sure the right-hand side is also multilinear, and that whenever you plug in a Boolean evaluation point, they agree. And because multilinear extensions are unique, if I give you two multilinear polynomials and they agree over the Boolean hypercube, they must be the same thing. And this is just an exercise to do, and it's just holds basically because we just have the same little block repeated many times. And in this way, you actually can more or less avoid the cost of any additional sum checks, right? So you virtualize A, B, and C completely for free. Okay, questions about this? Okay, so
Do this when A is not a structure.
if A is completely unstructured, no. And in fact, then the verifier will not even be able to quickly on its own get, this evaluation from the first, is that the second? Yeah.
So then you're assuming something about the circuit that's being proven, right?
Yes, yeah.
I guess ZKVMs would have this.
Yeah, exactly. So ZKVMs, which I will talk about, always have the structure. And we've been taught, I've mentioned kind of repeatedly how all comparisons are super complicated, right? People have this view that ZKVMs have a lot of overhead for the prover. ZKVMs, the prover is proving it correctly ran a computer program specified for a simple CPU, kind of step by step by step. And there is this view, which definitely has some merit to it, that there's a lot of overhead to that, like to prove you ran like fetch, decode, execute over and over and over again if you didn't necessarily have to. Okay, but there's also a countervailing point, which is that much bigger statements has a ton of repeated structure in it. And so even though it's bigger, if you can kind of prove each step of that statement faster, you actually might come out ahead. And some of the ZKVM teams claim they've found that, that like going through the ZKVM actually gets a faster prover than going through hand-coded circuits or something. So yeah, so repeated structure, really important to exploit. And I'll say more about that in the last, 30 minutes. Other questions? Okay, all right, so let me summarize kind of what the main takeaways from this point of the talk. At this point, we're sort of reached the year 2020. So with appropriate commitment schemes, zeros are free to commit to, small values are cheap to commit to, and repeated structure in computation can be exploited for major performance gains for the prover. So now the remainder of the talk, I want to explain kind of how to leverage these properties to the extreme, okay? And also in the process cover recent trends in SNARK design. All right, so let's start with these ZKVMs. So I just mentioned this, but a ZKVM is a SNARK in which the prover proves it correctly ran a computer program that's kind of specified for a very simple CPU architecture. Right, so SNARK people use the terms like CPU and virtual machine and instruction set architecture interchangeably. Probably the computer architecture people are going crazy. I don't know, no one's ever complained to me though. And so, yeah, you're just proving, like, what does a VM do? It calls, like, fetch the next instruction to execute, decode that instruction, and then execute that instruction over and over and over again. And, it sort of also does reads and writes to registers in RAM, right? Like computers have memories, and they just call fetch, decode, execute, and do reads and writes to those memories. Okay, and so this is the embodiment of the second slide in the first hour, where I said we want developers to be able to just write witness checking computer programs and not have to worry about how SNARKs work at all. This is sort of the same way people will write computer programs and then it gets compiled down to machine code to run on your laptop. This is like here's the machine, right? It's the virtual machine here, and then you prove you ran the virtual machine correctly. Okay. Now the challenge here is the prover overhead, and also these are very, very complicated protocols that are still definitely full of bugs today. And so how do we deal with that? All right, some kind of lower level trends in ZKVM design. There's been a lot of focus on something called the RISC-V instruction set architecture. This is just a very simple instruction set that was designed by the computer architecture community. It's open source. It's really impressive how competitive this architecture can be with more complicated things like what your laptop runs, despite being so much simpler. And I'd say that the reason to focus on it for ZKVMs are twofold. So I think there's very good reason to not invent our own ISAs, right? Because the computer architecture community has tons of tooling, compilers, and stuff for the ISAs they've been developing for decades, right? And this is the simplest one that meets those bills. So we kind of want to pick the simplest one where we can take advantage of the existing tooling. That would be RISC-V. I also think it's very friendly to snark proving. This is a very controversial opinion, but and we'll see why I feel this way in a few minutes. Okay, so that's one focus, RISC-V. There's lots of ZKVMs that are not focused on RISC-V, but it's definitely the dominant one right now. And then the other main focus is this particular application called, I mentioned it earlier, real-time proving of Ethereum blocks. People think this is key to sort of letting Ethereum process more transactions in a given amount of time, and letting different layer 2 blockchains that settle on Ethereum like interoperate nicer and things like that. Now, so I do want to give a sense of just how big are the computations people are proving today, and the answer is that like one Ethereum block today, if it's full, not all of the blocks are full, but the full ones, they're on the order of 1 billion RISC-V cycles. Okay, so when we talk about cycle counts, 1 billion. Yeah. Okay.
What is real-time proving? Is it the same as IVC?
Real-time proving just means you get the proof for a block in under 12 seconds, which is when the next block comes in. And I think really for the applications people want, you actually want to go below, significantly below 12 seconds. But we're calling it 12 seconds for now.
It's not the same as IVC.
So once you have real-time proving of Ethereum blocks, you can then kind of try to turn Ethereum into a succinct blockchain on top of that, where you take the proof of the latest block, and then you kind of combine it with the proof of all the previous blocks up until that point, and now you have a proof of all of Ethereum's history up till now, and that is IVC. So real-time proving of Ethereum blocks is like a stepping stone to full IVC of it.
All of this is not tied to ZKVM, right?
No, you don't have to do this with the ZKVM, but people tried doing this for years without ZKVMs and found challenges. Now, of course,
Other challenges?
Major both performance and the complexity of like the circuits they were writing and things. Now, I will say the EVM is a VM, so there's going to be a VM abstraction somewhere, no matter what. Like the definition of the problem has a VM baked into it. But it's funny, we're proving the EVM, the Ethereum virtual machine, by turning it into the RISC-V virtual machine. So we're kind of emulating the EVM in RISC-V, sort of, and then proving the RISC-V. And we've found this to just be working out pretty well. Again, I think RISC-V is pretty snark friendly, even though many people seem to disagree with me. And so, yeah.
I guess like the point is that the fact that you want high-level programming language, it doesn't necessarily mean that it needs to be compiled.
You're right.
ZKVM.
You're right.
It's not whether the proof instructions are known ahead of time, whether we need the unit.
Yeah, you're right. You're right. And so my view of this is the end game. People kind of hate that word because you never get to the end. The end game will be to not have a pure VM abstraction. In fact, people are already moving beyond a pure VM abstraction in their ZKVMs, right? The Ethereum, like mostly what's getting proved is like hashes or digital signatures, and so they're kind of adding the hashes and digital signatures as a primitive instruction to RISC-V. And that's really, starting to move outside of a VM abstraction even.
I just want to separate the need for a high-level programming language from ZKVM because they're completely two different things.
Yeah, yes, that's correct. And we can keep them separate. And so here's my view, okay? By designing the fastest ZKVM, we will unlock the right proving techniques, and there will be benefits to it. In some cases, like the EVM application, really there is a VM somewhere in the definition of the problem, right? But then snark provers do not have to, like, ultimately you just want to make sure like the output of the program is correct. You don't need to make sure the prover correctly ran the program step by step in pure RISC-V, right? So in the end game, we probably move well beyond a pure VM abstraction, but by focusing on like, RISC-V ZKVMs, we are going to address a lot of the problems about how do you compare proof system A to proof system B. We're going to unlock the right techniques. And then once we have really good ZKVMs, we'll try to, see what is the right way to move potentially beyond a pure VM abstraction.
Maybe the end word is not to like compile every application to the same backend. So like, I feel like if let's say system A is better for application A, system B is better for application B, and forcing them to like compile to this thing is like misleading, right?
So I think the right proof machinery is going to be largely application independent, and things will change only if, whether, recursion, proving a proof would be a bottleneck, that you're not willing to pay, that might change how you do things. I don't think it's completely one size fits all, and I don't think we will ultimately wind up purely with ZKVMs. But this is really, at the moment, the only, well-developed, scalable way to turn arbitrary high-level computer programs into things we can actually get proofs out of right now. And we should see it to the end before we, figure out how to go beyond that. But no, you're definitely right to, you do not have to, high-level computer programs and VM abstractions do not, one does not force the other or vice versa. All right, so yeah, just so you sort of know what's going on in this space, there's like 25 independent ZKVM teams all trying to prove Ethereum in real time today. Now, I will give, in terms of the techniques they're using, so at this point, I guess 5 of the 25 are sum check based, and all of the rest are mostly using like univariate polynomials and quotienting. Some of the rest are kind of taking a hybrid approach. They'll sum check some parts of the statements, but still commit to univariate things and kind of switch at the last second from multivariate to univariate and stuff. Of course, I personally think you're getting a tiny fraction of the benefits of sum check if you do a hybrid thing, and you should just kind of go all sum check. So Jolt is, I've been working on this for 2 years. I will tell you some about the Jolt project now. We're using elliptic curve commitments. Petra and RISC-0 are switching to these binary field hashing commitments to get fast commitments to small values. SP1 Hypercube and Sino, they are using hashing-based commitments, but not over binary fields. Sino is GKR-based. SP1 has its own polynomial IOP. Yeah.
Any inherent reason why ZKVM use different techniques than
people think, some techniques, people have different opinions about what's faster and simpler. That's it.
Different techniques for ZKVM versus circus-based.
Well, I mean, yeah, so the big downside of circuits is that a developer has to sit there and sort of specify the circuit.
You can try to write a compiler somewhere.
Right. And so yeah. So people have designed what they call ZK DSLs, which vary in how high level or low level they are. So a lot of the popular and older ones, you really were writing down the circuit like one gate at a time. And more recent ones, like Noor, to name just one, is kind of higher level, and people seem to like that. But you're still not writing arbitrary high-level computer programs. You're designing your own compilers, all of this stuff. So, people have debates all the time today, like official debates. ZK DSLs versus ZKVMs.
That's a different question.
Yeah.
For the technique-wise.
Yeah.
Is the reason why ZKVM going to use different techniques
so
proof than the circuit?
Yeah, so no, it's the proof machinery is the same, but the ZKVMs, they have a lot more repeated structure in them, and people should be exploiting that. And so that's actually most of what I'm going to tell you about is how do I think you should exploit the repeated structure. Yeah. All right, so yeah, so let me tell you a little bit about Jolt. You could consider this a case study of just like one ZKVM. Obviously, I've been working on it for 2 years. I think it's like a very good approach to ZKVMs. But yeah, there are 24 others. So there are alternate approaches, and keep that in mind. Okay, so Jolt targets RISC-V, and it's sort of uniquely designed around the sumcheck protocol, which now there are 4 other projects also designed around. But it's still unique in its use of what are called lookup arguments and elliptic curve commitments. And I will explain shortly what those are. You know, I think it's fast on CPUs right now. It has state-of-the-art performance. It's also, I think, simpler, uniquely simpler. And again, I'll explain all of this, why that's the case. So it sort of has three components, right? Remember, VMs have a few components, right? There's a memory, there's like registers and RAM, right? The VM like has a memory it reads and writes from, right? And then there's you know, the computer program is like specified, you know, there's like machine code or byte code. And you know, the program is just calling like fetch, decode, execute over and over again, where you know there's a program counter which tells it like which line of the byte code to execute next, and it sort of looks up that line of the byte code, and you know that line of the byte code tells it, you know, oh, let's execute this primitive instruction, and you know the first input is stored in this register, and the second input is stored in that register, and save the result in this destination register, right? So yeah, so the way we handle primitive instruction execution is via what I call a batch evaluation argument. The community calls them lookup arguments, and they're the same thing. And I think the batch evaluation perspective is a better match for the ZKVM context, and you'll see why soon. So that's, yeah, so this is called shout. It's a new batch evaluation argument, new lookup argument. That's how Jolt executes primitive instructions. The machine's registers and RAMs are handled by a companion argument for read-write memory called twist. Okay, so batch evaluation arguments are actually the same as read-only memory, and you know twist handles read-write memory. Okay, and then there is still a circuit or a constraint system there, but it's very minimal. It's only got like 30 constraints per cycle, and kind of what it's there to do is kind of make sure you run each primitive instruction on the right inputs at each cycle, and save the results in the right, you know, in the right destination register. So it's there to just like link it's sort of the difference between like batch, we talked about batch NP and general NP before, right? It's like these things are like batch, right? And then this is general. This is how you make sure that you're feeding the right inputs to each instance in the batch. Okay. And then we apply something called Spartan to prove that constraint system. All right, so here's it in a picture, right? Like, you know, twist is proving registers and RAM are all being maintained correctly by the prover. And then shout is proving that each primitive instruction is executed correctly, and also that every lookup into bytecode is answered correctly. And then, you know, they're all kind of linked together to make sure they're all getting run on the right things by the circuit. But the circuit is very, very minimal. Okay. Questions about that? There is a sequentiality aspect to it, but everything is proved kind of all at once.
How is it encoded in the?
Yeah, I mean, so it's like, you know, there's 30 constraints per cycle, and so you kind of view and by the way, this is where the block diagonal constraint system comes from. And so you view like the first 30 constraints as capturing cycle 1, and the next 30 constraints capturing cycle 2, and all of that. Does that answer the question? Okay, so but let's talk about these batch evaluation arguments and you know this alternate perspective of the same primitive, you know, as read-only memory checking or lookup arguments. And this is the main other thing I wanted to cover. How much time should I take now?
We can go maybe 10 to 15 minutes beyond.
Oh, okay.
Late.
All right, so I should just don't worry about it. So let me know when I should start worrying about it. Okay. All right, so batch evaluation, you know, again, we talked about this notion in the morning, but in the context of NP, here it's P, right? So we have a simple function F. Now in a ZKVM context, this would be like a primitive instruction for the VM, right? This is something your computer does in one cycle, basically. Okay, so very simple. And it takes two inputs, they're both B-bit values, right? So in practice, you know, each of these is like 32 bits or 64 bits or something. Okay, and we just want to evaluate the simple function on, you know, T different inputs, right? So think of the prover as having, say, committed to, you know, for each instance of the function, 2 inputs and a claimed output, right? And so the prover is claiming, you know, it's already committed to, you know, a vector x of length t, y of length t, and z of length t, and is claiming that, hey, for each I from 1 to t, sorry, this should say zi equals f of xi comma yi. Okay, so the Z's are the claimed outputs. Okay. All right, so the standard way to prove this, like the prevailing way, basically what every ZKVM other than Jolt does today, is they just basically take a circuit that computes F and they repeat it T times, right?
What is the ZI comment? Is it like ZI equals to F of Xi, Yi, or?
Yeah, and there's a typo, sorry. So this should say, the claim is that for each I, ZI is F applied to Xi comma Yi. So yeah, just a typo. Yeah. Yeah, so Xi, Yi are the claimed, are the inputs to the ith copy of F. Zi is the claimed output. Right, and so, yeah, so you just apply a snark to this giant, you know, I call it like a data parallel circuit, T copies of the same little simple subcircuit, yeah. Okay, and you know, this has two issues. So one is somebody has to, you know, specify this circuit, right? So there's some developer there who like looked at each RISC-V primitive instruction and like turned it into a circuit. And then secondly, you know, even the fastest snarks, so like this GKR protocol that only is sum check based, no commitments or anything, that's still going to pay like the prover's 6 field operations per gate. Okay, so that's still like a meaningful expense, and then that's assuming the circuit's deterministic, right? If the circuit takes untrusted advice, the prover also has to commit to the untrusted advice. That's even more work for the prover. Okay. So batch evaluation arguments, the idea is if the batch size T is big enough, you can just get rid of the circuits, okay? And this makes things both simpler and faster, okay? And so like, let me give, let's focus on simplicity for a section, okay? So ultimately the verifier in you know, in shout, in this new batch evaluation argument, it just takes the multilinear extension of F and evaluates it at one random point. Okay, so if you look at in Jolt, this is one of the more complicated RISC-V primitive instructions. It's set less than unsigned. You just you know, you're asking is X less than Y, you know, as integers. You know, the old way you'd have to specify a whole circuit computing less than, and you have a problem where, you know, X and Y are committed as like one number each, but you know, in order to turn X less than Y into like a low degree operations, you need to do a bit decomposition, or you know, that's expensive and all this stuff, right? So in Jolt, this is the whole description for the verifier of this primitive instruction. It's just, you know, one for loop basically to evaluate the multilinear extension of F, right? So rather than like hundreds and hundreds of lines of code, it's like 5 lines of code. So on the simplicity side, this is a significant positive, right? Okay, but now let's talk about the performance side. So the idea of a batch evaluation argument is there's some kind of fixed cost that's independent of the batch size, right? And then some cost that grows with the batch size, okay? And they're in tension with each other. So, you know, the lower you make the fixed cost, so there's this parameter C. So the bigger you make C, the lower you're making the fixed cost, but the more you're making the per evaluation cost, okay? Now, so think of this capital N here, you know, so if you're viewing, maybe I'll tell you how to think of this as read-only memory checking, right? Just imagine a memory that is storing every single possible evaluation of F. Now we're just doing lookups into that memory. So this capital N is like the size of that memory, okay? And so, yeah, you know, for RISC-V with 32-bit data types, the size of this memory is 2 to the 64. If I set C to be 4, this is like 2 to the 16, right? But remember, the number of cycles we want to run our VM for is like 1 billion or even more, right? Proving an Ethereum block is like 1 billion cycles. 2 to the 16 is well under 1 million, right? So you set C equals 4, this fixed cost is like nothing compared to this order, you know, CT cost. Just T is like 1 billion, and this is like 1 million, and yeah, it's fine. So that's the idea. All right, and yeah, okay, so. Right, okay, and so if you look at the prover cost in shout, you know, you should ignore the fixed cost because it's low order, you know, for anything but a toy program. And then this cost concretely turns into well under 100 field multiplications for the prover per evaluation. Okay, so you can compare that to the circuit approach. The circuit approach, it's 6 field multiplications for the prover per gate in the circuit. That's with like the GKR protocol. It's higher, you know, if you know, there's untrusted device and all this stuff. So the prover cost in shout per evaluation is the same cost as like the circuit approach for like a 10-gate circuit. Okay, and you can't really do anything in a 10-gate circuit other than just native field addition multiplication, right? Like that's one gate, and there's really not much else you can do. Almost anything requires some kind of lim or bit decomposition, and you're instantly way above, like 10 gates or something. So yeah, so this is both simpler and more performative. That's my view of Shout. And now I just want to, I want to tell you kind of the old way of doing lookup arguments and the Shout way of doing lookup arguments. And that's going to get into this whole, why committing to zeros for free is so important and stuff like that. Okay, so this is the old way of doing lookup arguments as of, January when Shout came out. This is a little easier to describe if we use the read-only memory perspective. Again, they're equivalent. So we have a read-only memory, I'm going to call it capital M. That's like the contents of memory. And the size of that memory is capital N. Okay, and so the prover has committed to a bunch of indices. These are like the addresses we're reading. Think of this is equivalent to like the inputs to the primitive instructions in RISC-V. Yeah. Before it was x comma y, but now for notational simplicity, it's just there's an x. Yeah. And then there's z. Okay. And so the claim is that for I equals 1 to t for each entry of x and z, zi is just what the memory stores at cell xi. Yeah.
Is M more or less what you call F on the previous slide?
Yeah. M is storing all evaluations of F. Yeah. That's the correspondence between this view and the other view. Yeah. But again, it's
M is a truth table.
Yeah, exactly. It's the same primitive, just viewed in two different ways. Yeah. Okay, so the way we used to do lookup arguments, assuming people like Shout, is the following. You somehow identify two vectors A and B, which are both of size typically, order n plus t. So there's like a table size cost and like a number of reads into the table cost, such that P's original claim is valid if and only if these two things are permutations of each other. Okay, and I can sketch there are many different ways you can do this, reduction from the original claim to permutation checking. But let me just give you the basic idea underlying all of them. Imagine that n is tiny. It's so tiny, I'm actually willing to tell you one number per memory cell. Okay, so what I'm going to do as the prover is I'm going to explicitly send to the verifier a count for each cell, like the number of times it was read. Okay, let's say, obviously if the memory is big, you don't want to do this, right? You'd lose the signets, but imagine the memory is tiny, now you can do this, okay? So then you can define, and I'm hiding things here a little bit because, here I said A and B, well, yeah, okay, these are going to be vectors of tuples in this little sketch rather than individual field elements. So we can let A be the vector whose ith entry is xi comma zi. Okay, so these are like the actual addresses and the claimed answers. And B be the vector where I actually take the table entries and repeat them the certain number of times. Okay, and like it's easy to see that A and B under this definition are permutations of each other if and only if like the reads are all correct. Yeah, any questions? Okay, so like all of these lookup arguments kind of pre-Shout. They all have multiplicities, these counts arising somewhere in them. But they work very hard in terms of the protocol designers being very clever to get rid of this need for the prover to explicitly send the multiplicities. Instead, you really only want the prover to commit to the multiplicities, but that would create problems unless you're clever. So anyway, okay, so there's the question then of now I have these two vectors A and B. How do I check that they're permutations of each other? Okay, and here, this is an old trick. I guess it dates back to Lipton, 89. You just interpret the entries of A and B as the roots of a univariate polynomial, and you evaluate that polynomial at a point. Right? If I reorder the roots of a polynomial, I don't change the polynomial, and so it's going to spit out the same thing at that point. And so you wind up computing this big product. This L is like, remember, table size plus number of lookups up to a constant factor. And so computing a giant product like this, it's called a grand product argument. Okay, and now if you're using the sum check protocol, which is what you should do for the fastest possible prover, you kind of have two options. So there's the GKR protocol applied to a circuit that just is a binary tree of multiplication gates, one for the left-hand side and one for the right-hand side. Now that's going to be pretty fast for the prover. You know, the circuit is so simple that you actually go down to like from 6 to 3 field multiplications per gate. But the proofs are going to be a little bit big because you're running sum check once per layer of the circuit with that protocol. And there's an alternate approach. Sorry, I thought that was off. There's an alternate approach where the prover commits to a value for every gate in the circuit, and that brings the proof size down from log squared to log. Okay, but here's the problem with that approach. While even if the entries of A and B are small, okay, and if like your table only stores small values, and they will be small, the interior gates of this multiplication circuit involve the random value. And so committing to those values is slow. And you actually see when you implement this, you know, it's slow. It's like, this is the bottleneck. It's like 10 times slower for the prover. So you get smaller proofs, but a much slower prover. Okay. So this is like the old way of doing things. You know, a lot of lookup arguments use univariate techniques, and that just sort of, you know, it's the same, everything's the same except the grand product arguments, and then there's a quotient polynomial, and that makes the prover slower and things like that. Okay, so now I'll tell you how shout works. Now, one nice thing about shout is it makes a lot of things virtual that previously had to be committed. So I defined the problem before. I'm back to the batch evaluation viewpoint, where, you know, xi, yi, and zi, they were all committed, right? In shout, they'll actually all be virtual. Now, you do have to, you know, commit to the addresses, the inputs to f somehow. Zi literally will just, you know, not be committed at all. So the way we actually wind up committing to the inputs xi, yi to f is via what's called one-hot format, okay? So, you know, this means that this will sound kind of terrible, but we'll see it's actually not terrible. You know, if you know, let's say xi is a 32-bit value and yi is a 32-bit value, okay? That means there are 2 to the 64 possible inputs to f. The way I'm going to specify xi and yi when I commit is I'm going to have a vector of length 2 to the 64. And it's going to have exactly 1, 1, and the rest is 0. Okay. So this RA is for read address. I'm like mixing the two views of batch evaluation or memory checking. So yeah, you know, if I feed into RA, like I call it a cycle, like which read operation am I looking at, and an address, which is like 64 bits, say, it will spit out 1, you know, if that is the unique 1 in the I vector of length 2 to the 64, and it'll spit out 0, 0 otherwise. Okay, so it's a huge vector we're committing to, you know, length 2 to the 64 per lookup. So it's like t times 2 to the 64 values committed. So huge, but very sparse, only t non-zeros. Why do this? Once you do this, everything you want in the prover's claim is just nice and low degree in the simplest kind of constraints you can ever imagine, right? In particular, the true output multilinear extension evaluated at any input is just the sum over all. So think of this as you're saying, I'm summing over, okay, z twiddle of I, if I is Boolean, 0, 1 valued, is like the, you know, the true value returned by the ith read by the ith evaluation of f. Okay, and that is now a sum over all possible memory locations of the one-hot encoding of the ith memory cell times f at that cell, right? And yeah, this is just killing any k that's not read at cycle I, and for the k that is read at cycle I, it spits out 1, and then you get f of k. Yeah, and so, you know, we've made z virtual, like we're done. That's it. You know, so when the you know, jolt verifier needs to evaluate the multilinear extension to z at a random point, z wasn't even committed, no problem. We just apply sum check to compute the sum. At the end of that sum check, it has to evaluate RA twiddle at a random point and F twiddle at a random point. RA twiddle was committed, so the verifier is going to get it from there. And all the RISC-V instructions, F twiddle, the verifier can compute in, you know, 64 field operations or something tiny like that. Yeah. So from the verifier's perspective, we've reduced evaluating evaluating f at t different inputs to evaluating f at just one input. That's really, it's a reduction from many to one. Okay, so what are the remaining challenges? I mean, you know, this was kind of ridiculous that I said the prover is going to commit to vectors of length 2 to the 64, right? How can you do that? And so that's one issue. And then also the sum is over 2 to the 64 terms. So that's another issue. And for both issues, we're saved by the extreme sparsity. Yeah. So focusing on the sum first, you know, what's going on is, you know, all but t terms of the sum are 0. I mean, that's it. Let's see. All but t, yeah, all but t, yeah, it turns out all but t terms of that sum are 0. And so you can apply the sparse sum check prover algorithm from 2011, and now your time is proportional to t. Okay, but you know, remember I said that algorithm takes time t per round, and there's like, you know, 32 or 64 rounds, or so, I guess 64 rounds. So we're not happy with that. It turns out that these primitive instructions for RISC-V are so structured that you can get rid of this factor that depends on like the machine word size and really get these costs I stated before. Okay. And so this is the reason I say this is one reason I say RISC-V actually is very snark friendly. You can handle every RISC-V primitive instruction by, you know, something like shout. You could imagine adding even more instructions that are more complicated and shout might still apply. You could, yeah, go ahead.
So should it be surprising that all of these instructions MOEs are so simple?
Yeah, so it's a great question. It's actually philosophically interesting, right? Here's my take. What is it that makes an MLE fast to evaluate? It's roughly that the function, the output of the function is just very simple as a function of the bits of the input. Okay.
Like a small circuit.
Yeah, you know, there's results that actually characterize, you know, when our MLE is fast to evaluate in terms of read-once branching programs, but that's like sort of a kind of circuit. It's, you know, very limited computational model. But, you know, just waving my hands like crazy, you know, it's like functions that, you know, if you take the bits of the input and you just do some simple things bit by bit to get the output, that's going to have a nice MLE. And that's exactly the same kinds of functions that computer architecture people put as primitive instructions. You know, is X less than Y, you know.
Happy coincidence that both the computer architecture people like this sort of thing.
Yeah, there's a good question about whether, you know, there's a deeper reason than happy coincidence. Now, one thing I will say is the following. It's worth explaining how we handle addition and multiplication, okay? Because those are not simple functions of the bits of the input, right? Like if you know, yeah, anyway. So the way we handle them, they're kind of unique. We handle them in a unique way. Is we just do the operation natively in the field. And this is a benefit of working over fields of large characteristic the way elliptic curves do. So RISC-V says, hey, if I add two 32-bit numbers or multiply them, right, any overflow bits, so if bits 33 and up are non-zero, I should throw them away. So if I do the operation natively in the field and the field's big characteristic, there's no overflow. You don't overflow the field. So then we use lookups. So we just do the operation in the field, you know, but now RISC-V says we got to figure out the overflow bits and throw them away. We just figure out the overflow bits with lookups. Okay. So that is the one example where you have to be a little clever to make everything work out. But here, yeah, for something like less than or, you know, bitwise XOR, you know, they're simple bitwise things. So it all works out. Yeah. Yeah.
Okay, how is this different from random linear combination?
Random linear combination of what?
Suppose the pair, key-value pairs.
Yeah, okay. So there's a big sum here, and this these are not random. They become random. So there obviously is randomness in the protocol, but you know, I don't want to say this. I mean, okay, so maybe the proposal of random linear combination is a little bit vague, right? You know, the original claim is that, you know, like the ith evaluation of z is equal to like the correct output of f on a given input where the input is specified by this RA thing, right? And so, I guess a random linear combination of those claims would amount to subtracting the left-hand side from the right-hand side so that the prover's honest, everything's 0, and then taking a big random linear combination of them. We're actually doing something very similar to that, okay? So, the thing I covered before part 2 of the talk, maybe I shouldn't go all the way back, but I don't think it's that far. Oh, it's farther than I thought. This thing. This was like basically a random linear combination of constraints. The way we arrived at shout was we did that. We did this. And then we realized what we were actually doing was making the z polynomial virtual. Okay, so it's like, if you just do this, I think you have to commit to z. You have to commit to z, and then you make, anyway, it turns out you don't even have to commit to z. Yeah, so we're doing something very similar to the random linear combination proposal. I just sort of optimize. Okay. Other questions? Yeah.
You also need to prove that RA 0, RA or 0.
Yeah. So you have to prove that RA is 1 hot. Okay, and that is also concerning because RA is so big, but you can leverage the 1 hot structure to do that in the same runtime for the prover. So, and I'm not gonna, not gonna tell you how to do that, but yeah, so you can prove 1 hotness in this time bound as well. But you're totally right. Like, you can't trust the prover to commit to something 1 hot, and if it committed to something not 1 hot, it could cheat. Yeah, check it. Okay, yeah, let me try to wrap up. Right, okay, so I told you how you can handle the sum over 2 to the 64 terms just because almost all the terms are 0. Okay, how do you commit to a vector that is so big? In a sentence, you only have to pay for the non-zeros in the commitment if you have free commitments to zeros. Now, even that is not quite true, okay? Because if you have a linear size commitment key, you can't tolerate a commitment key of size 2 to 64. Also, the evaluation proofs can hurt you. They can be, expensive enough that still is not doable. So there are a few things you can do, and you should combine all of them, right? So one thing you can do is you can use something like Dory, where the commitment key is square root size instead of linear, and the evaluation proofs are very fast. Not that much more work than just computing the right evaluation, a little bit more work. But Dory alone is still not enough, so we give a way to sort of, bridge the gap. And here we leverage multiplicative structure in anything 1 hot. Okay, so rather than the prover committing to, t things that are each of size n, the prover commits to t things that are each of size n to the 1 over c. Feels like we're doing the same thing over and over again, but and now every entry of the 1 hot thing is now just the product of entries in the smaller things, right? So you kind of define the 1 hot thing to just be the tensor product of these smaller 1 hot things. You tensor product 1 hot things, you get a 1 hot thing, and yeah. And in this way, you pay another sum check, and but it's pretty cheap, and you can mitigate the whole 2 to the 64 thing, yeah. And yeah, so we almost are done in, today Jolt uses an older lookup argument called lasso. We're switching over to shout, and it's read-write memory analog twist. And Jolt was using GKR for these grand products that come up in the permutation checks. And again, they have pretty big proofs. So with shout, there's much fewer sum checks, and so the proofs are coming down by 5x. The prover is speeding up in different components of Jolt from between factor 7 to factor 2 or so. And it just seems to be a more performative way to do batch evaluation or lookups. But my bigger point is just, no matter how you do batch evaluation or lookups, ZKVMs, they by definition are doing the same simple things over and over again. You should be using batch protocols, and that means avoiding circuits and taking advantage of the repeated structure. Hopefully this talk is convincing in that regard. Okay, I should wrap up. Okay. Another benefit of twist and shout, remember the sparse sum check proving algorithm is consistent with the streaming prover, small space prover. So today people control prover space by breaking long VM executions into small pieces and proving each piece separately and aggregating the results, we are going to get rid of that without a major hit to prover time, and it's because things are sparse, and the sparse prover is consistent with small space proving. So that's what I was getting at in the first talk, where I said I want to try to minimize the use of recursion. Okay, so just here's my final slide of takeaways. So I think the sum check prover, the sum check protocol is key to fast prover. And there's this delicate interplay between the properties the commitment scheme has and the properties the PIOP has. So you really want the PIOP to avoid forcing the prover to commit to random values, and then you want the commitment scheme to be fast when the prover only commits to small values and to zeros. And I think the community is still internalizing some of these messages, so you'll see transitions happening from univariate polynomials to multilinear. I'm hoping from hashing-based schemes to commitment schemes to curves or lattices. I'm hoping there will be less recursion moving forward. And just putting some open questions up here. Yeah, lattice-based polynomial commitment schemes I've said a bunch about. So I'd love to see more interest in making those practical. Formal verification, I think, is the only way we can get the bugs out of these protocols. They're just so much more complicated than cryptography that we've deployed today. And ZK is kind of leading the way here, right? People want this kind of programmable cryptography revolution with MPC and FHE, where you can prove any computer program, basically. And ZK is at the vanguard because it's the most efficient of the three, basically. And so this is a major open question, and it's intellectually interesting in addition to practically important, right? We're going to have these protocols very clean and well understood to put them into formal verification tooling. And then there's this issue, once the bugs are gone, the main concern will turn to how we don't have plain model security analyses of all of these protocols. And so I'd love to see more work on that, as well as the speakers from this morning also highlighted. So, all right, thanks a lot.
Questions?
Thank you.
I'm sorry, when you give